Hello class, welcome back. In this session, we're going to talk about operation amplifiers. What is an operation amplifier? If you look at the basic operation amplifier in a chip, it would look like the 741 IC. Where is it used? It's used to measure voltages. Example, in this case, you have EMG electrodes that can measure your muscle activity. In other words, when you tighten your muscle, I want to measure it. Or if your heart is beating and your doctor wants to know your heart rate, they stick these electrodes onto your skin. And these voltages are very low voltages. If I have to measure the slow voltages, I need to have a very precise amplifier that can amplify the signals to give me a decent signal that I can connect to a recording device or a monitoring device. I could use those, and those are the ones that are available in such boards, precision amplifiers. Yes, and you also have requirements that need to work with, example, in temperature measurement, in this case, a thermocouple. There's a small voltage that's been generated between these two different metals when I keep this temperature probe on a surface to measure its temperature. And such precise low voltages can be measured with an operation amplifier. Let's look at it in detail in this session. Looking at our syllabus, you would see that we have the block diagram, the configuration, the use of an op-amp, and its inverting and non-inverting operation, summing, voltage to current conversion, current to voltage conversion, differentiator, comparator, Wien bridge oscillator, and Schmitt trigger, and an instrument amplifier. We'll go through them one at a time. Let's look at it and what does it look like in reality. So let's look at it one at a time. Let's look at a typical operation amplifier block diagram. An operation amplifier has a symbol. It looks like this triangle with two inputs and one output. So why do you have two inputs? One is your inverting input and one is your non-inverting input. If I feed input to the inverting input, the output would be inverted. The non-inverting input, the output would not be inverted. Let's look at that in a little bit of detail. Looking at a block diagram, it's actually made out of transistors. Let's look at that again. So it's a differential amplifier. So there are two inputs, both the signals are amplified, and the difference of the output goes to the next stage. Now you increase the gain of the stage here, then you shift levels. In case if it's less than 0, you go negative. If it's more greater than 0, you make it positive. And if it's exactly equal, you level it, set it at 0. This is level shifting. Then you have an emitter follower to couple the stage to be able to drive your outputs. So that's your output line. So this is the block diagram of your operation amplifier. Now what does it look like as a circuit? Let's look at it one at a time. Now the operation amplifier Now let's look at the internals of an operation amplifier. We saw the IC 741, the small 8-pin IC. Now this is exactly what's inside it. Now if you notice it, the operation amplifier to operate, you need to have two voltages. You need plus voltages, plus 15 and minus 15. You also need your input, your inverting input, your non-inverting input. So those are the ones. One is grounded and one is connected to your 120 hertz input, and you have your output pin. So you also have other controls of your IC, and some of the pins may not be in use. Now, looking at the internals of the op-amp, you see that it's made out of transistors. So this is an extension of transistors where the entire circuit of an operation amplifier circuit is embedded into a single chip, or even right down to a small dot in a smaller form factor. So to understand it, let's look at it. Let's look at the symbol again. So for this operation amplifier, this is the symbol of the operation amplifier. I have two inputs, your inverting and non-inverting, and your output. If the difference between the two inputs is equal to 0, the output is 0. The moment I have the input increase or decrease, if I increase it, if inverted, in the non-inverting input is increased, the output goes positive, or if it's equal, it stays 0. If it's not equal to, if it goes lower, it becomes negative. How is this negative 15 and positive 15 coming in? It's your power supply, your plus 15 and minus 15 that you connect to it. So what does it do? It's a differential amplifier. In other words, it's got two inputs, two differential inputs, and based on this input, the output switches between logic high or logic low, plus 15 or minus 15 or 0. So okay, logics of high, low, or 0. Now, to understand this in detail, let's have a look at the application of the circuit in a different form factor. Now, looking at this, I'm giving a sine wave and it's able to generate a square wave for me. Now this sine wave is exactly what this operation amplifier is doing. And this input, you can see exactly which of the transistors turning on. Let's increase the simulation speed to see exactly how the input current flows between the different phases and how it does affect your operation. So you do see your plus voltage, your minus voltage. The red side is on the positive higher volt potential, and the green is higher potential, and the red is low potential. And which is the stage that turns on and turns off, and you can see the capacitors charging and discharging. Okay, over to an application. First application we're going to be looking at is an inverting amplifier. When we say inverting amplifier, the input is given to the op amp. In this case, I'm using a 40 Hertz AC input, and the voltage is about 5 volts, and my output is amplified. 5 volt has become 14.9 and is about 15 volt. But if you look at it, the voltage is dropping, it's rising. Now the output will be exactly opposite. In other words, if my input is high, output is low. If my output is high, input is low. So this is exactly called an inverting amplifier. In other words, my output is inverted with reference to the input. In other words, if when it's high, I follow the low, but it's based on the frequency, and this frequency is what is it is out of phase with this particular frequency of the input. So it only works with AC. In this case, we're not talking about inversion in DC. It can happen in DC also, but we're talking about the sine wave representation when it's in an AC circuit. Now let's look at it for a non-inverting input. In other words, when I have this configured this way, my output follows the input, but it also does the amplification. When it's high, it's high. When it's low, it's low. And it does have a non-inverted amplification. Another application, it's called a differentiator. You talk about mathematical differentiation. In electronics, analog electronics, operation amplifiers are capable of doing such operations. If I want to differentiate an input, in this case, I'm giving my input as a triangular sawtooth, a triangular wave, and my output is a rectangular wave. And this is possible with an operation amplifier. And this is a typical application of having a op amp used to differentiation in analog electronics. Now in this case, an integrator. I have integrated this stepped square input, and I've got a triangular output. The opposite of differentiation is integration. So this is how it's realized in the electronic form. Now you also have another application, it's a Schmitt trigger. If I want to trigger a particular, this is a summing amplifier. I have two inputs. One is a 200 Hertz sine wave. I also have a 20 Hertz square wave. Looking at this 20 Hertz square wave, it's pretty square and the frequency is low. My 200 Hertz sine wave is high frequency. Now, when I add these two, my differential amplifier is able to add them up. And you look at this output wave, it's a combination of these two waves. It's an addition of these two waves. Another application would be a differential amplifier, as we talked about earlier. In this case, I have two input waves, but in this case, one is a pure sine wave, 60 Hertz. The second one is a combination of a 60 Hertz sine wave and a 120 Hertz square wave. And that distorted wave is what's coming into the input, and my differential output, the difference between these two waves, is coming out as a square wave. So what happens when the voltages are exactly zero? It crosses the zero. When the voltages are different, and if this is greater, it switches on and goes high. When it's lower, it goes low, and it crosses a zero every time it switches over. So you get a square wave that crosses zero, and this is possible when the differential configuration of the amplifier. It's a simple circuit, and you'd be able to realize it in this form factor. Now let's look at another application, Schmitt trigger. When you want to trigger, example, an SCR precisely based on the waveform, this circuit is what can help you do it. Now you look at your input, it's an oscillated sine wave, and it's got two components in it. One is a 1 kilohertz and a 40 hertz combined together, and that input is fed to your op amp. Now your output is a trigger. Either you look at the output waveform, it's either low or it's high, low or high. It does not stop anywhere in between. And such an application is a trigger application for an operation amplifier. Now let's look at another application of an operation amplifier. An operation amplifier can generate a sine wave as an oscillator. In this case, this is a circuit called a Wien bridge oscillator, and this circuit is also called a Wheatstone bridge oscillator. A Wheatstone bridge oscillator, because it looks like a Wheatstone bridge, it has an RC in series, RC in parallel, and two other bridge resistors. When it's fed to an operation amplifier in this loop, in this configuration, you look at this violet color ring, it oscillates and generates a sine wave, and the frequency depends on these RC networks. Now, this is typical application of an oscillator used as a generator to generate a sine wave. And we could see this out. I could try to simulate it, but you can see the same circuit in a different form factor. In other words, you don't have to put it exactly in this diamond shape. It's just talking about the connection. You can also have this arms in parallel to this arm. In other words, it could be in parallel, but the configuration is similar. Okay, let's look at another consideration. Now in this case, when I want to talk about, as I talked about earlier, we talked about operation amplifiers to be able to do precise measurements or to precise amplification, like in the case of operating a thermocouple, or in the case of operating an input from an electrode from a medical instrument. So such measurements need to have precision boards that are designed to work with operation amplifiers that are designed to be able to amplify that precise low voltages and give it as a desirable value. So we did see the 741 IC. It's a small 8-pin IC. We saw the internal block diagram. It's made of transistors. So the entire circuit of transistors has been realized as a small single package. The truth is, the insides of this IC is actually a really small op amp in the center with all the breakout wires connected. So you have your power supply, you have your input pins, your output pins, and all that, and your ground pin, all that in such a small package. Yes? And why do I need to have op amps? Example, I need to measure the resistance of water and turn on a pump. Because how do I detect water levels? One of the simple methods is using wires as electrodes. I stick one water electrode right into the bottom of the tank and one electrode on the surface of the tank. The water level comes up, it touches that wire. I can measure the resistance of the water. And the moment I see the resistance, there's a small current that could be considered as an input, and that could be able to use to turn on an op amp. That small input is given to an op amp. Now in this case, I have 4 op amps in one small package. So this small, as I talked about the resistance of water, I'm using that to measure this. So I have 2 op amps, 2 inputs to measure the a tank water level, upper level and lower level. I have 2 inputs to measure the upper level and lower level of a sump. So if your tank is low, turn the pump on. If the tank is high, turn the pump off. If the sump is low, it's not safe to run the pump. Don't turn the pump on. If your tank is high, sump is high, it's safe to turn the pump on because you have enough water to run the pump. So what happens is these op amps give you a logic high or logic low. That is fed into your transistor. So this is a metal cap transistor. So you have 3 of them. I actually had one more, which I removed and desoldered it for another project. So this op amp output goes to your metal cap transistor. This transistor drives your relay, and this relay is what is used as a logic input for your PLC maybe, or another microcontroller, or maybe even directly drive a logic pump, logic controller for a pump. So this is how we could use an op amp. So precise measurements. In other words, it's a long wire from the pump controller all the way to the tank or to the sump, and that small signal can be amplified using an op amp to drive a transistor in case, and this transistor drives your relay to control your pumps or your logic controllers. Yes, let's go back to understanding how this is possible in a small form factor. So what does an op amp can do? Op amps can work on the voltage modes as an input or current modes. In other words, there are different classifications of designs. In other words, it can have voltage in, voltage out. In other words, it has high input impedance, does not draw much current. It's only a voltage signal. It's like having high pressure or low flow and voltage out, or it could be current in, current out. It could also work in the transconductance mode, which is high impedance on the input, low impedance on the output. In other words, voltage in, current out, or the reverse of that. Trans resistance. Low impedance on your input might be a series circuit, current in, voltage out. So these are the configurations it can work in. Now look at what an IC looks like. I talked about the IC, I talked about LM324. It's got 4 operation amplifiers inside a single small package. So example, now we talked about an application where I need to have a precision amplifier. I need 3 op amps. How can I get 3 op amps in a single to get the application of a precision amplifier? I would need an op amp that at least has 4. I use 3 of them to get the task done. Such a need for having multiple op amps in a single circuit, like how we have multiple transistors inside an op amp, multiple op amps to realize a single circuit. We use such ICs which has multiple op amps inside a single enclosed package. So we've seen how precision amplification can be done, differential operations, summing operations, integration, differentiation, and we've seen them with practical circuits. So the most important thing is you need to understand how the feedback loops are connected and how they are different from each other. Let's go back to see our functional system. So based on our syllabus, we need to understand what an operation amplifier is. We saw the block diagram, we saw the configuration and how it can be used. We saw the inverted output, the non-inverted output, summing when you summed up a square wave and a sine wave together, voltage to current input. In other words, let's look at this voltage to current and current to voltage in detail. Okay, later. Now we saw differentiators, the difference in output, comparators to compare two different inputs and give you an output. Wien bridge oscillator, we talked about the Wheatstone bridge based input in your RC network. Schmitt trigger to be able to trigger either high or low precisely. Instrument amplifiers. Let's look at the missing topic, which is voltage to current converters and current to voltage converters in detail. Now let's look at this circuit. This is a current to voltage source. In other words, now these is constant current sources, and this is I can get a constant current now. Now this is 2 milliamps. Now this is my input. Now based on this 2 milliamps, I want to get a precise voltage. In other words, I'm converting current into voltage. Let's switch this. Now current is 0, voltage is 0. The circuit that be able to convert this precise 2 milliamp current into voltage by using an operation amplifier is called current to voltage converter. In other words, I'm able to have a current. Current is, what is current? What is voltage? Current is like the flow of water in a pipe, and voltage is like the pressure that's built up, and you can feel the pressure inside the pipe. So when you have high voltage and low current, it also could be equal to low voltage and high current. It's like voltage into current is power. So flow and pressure totally talk about what is happening in the pipe. So this is talking about high flow to high voltage. In other words, here there's low impedance, here there's high impedance, and this conversion of low impedance to high impedance is what a current to voltage converter can do. Now in the opposite case, in this case, I have a constant current of 1.667 amps flowing through the circuit. Now this is my voltage reference. I have a negative voltage here and my grounded inputs to my operation amplifier. Now if I close this circuit, I would short circuit this resistor. Now when I short circuit this resistor, the current of exactly that was flowing through it earlier, which was 2 kilo ohms. Normally when you short circuit, the current would increase because the resistance has dropped in the circuit, but in this case, you look at it, it's exactly the same, 1.667 milliamps. Look at it again. In this case, when the switch is open, 1.667 milliamps flowing through the resistor. Though it is 2 kilo ohms, now it's short circuited, it's still flowing at 1.667 milliamps. You can see that below. Though the voltage is 0 across the resistor, the current still is maintained through the switch. This having a current, it's like a constant current source. Irrespective of the resistance that changes in the load, the current stays constant. So this is a kind of a circuit that you could use to ensure the current is fixed, and I'm having the voltage that I'm applied to the circuit now is become a constant current source. So how can operation amplifier be operated? Now I could have it configured in different configurations as voltage source, as a current source, and a current to voltage converter, and vice versa. And this is all possible with a simple operation amplifier that's designed to work in this particular form factor. So it all starts with a simple design based on transistors, and the development of this design has come about with the development of analog electronics to be able to do that in the recent days. Now the same concepts apply. The size of the devices have reduced. Operation amplifiers are even become better these days, and the levels at which it can operate has changed. Sometimes you can have operation amplifiers that don't need to have an external plus and minus power supply. For example, let's look at a power supply that I could typically use with an operation amplifier. In this case, I have a transformer. You've seen this earlier. It's a center tap transformer. In other words, this black wire is my ground. I could have plus 12 and minus 12. If I rectify this and I have dual power supplies, I would have a 0, plus 12 and minus 12 as a DC power supply being fed after rectification to my circuitry. Example, this operation amplifier. But these days, I could have a single power supply, and the single power supply using a voltage divider can be split into 2 power supplies and can be fed to my operation amplifier. So I don't need to give it the plus 12, minus 12, plus 15, minus 15 these days for operation amplifiers. Example, in this case, it's operating on 5 volt, and I don't have to give it dual power supplies, but it still does the job of precision amplification in this case of this AMG board. So I don't need to, I talked about it. You need, typically operation amplifiers need plus and minus voltages. Like in this centered Gibbs transformer, I give 230 volt input, I get 2 voltages output. Like I could use both these wires together. Consider this as 0, this will be plus 24. But in this case, this requires a plus and minus 12 or plus and minus 15 to operate. But these days, the development of voltage dividers and the precision low voltage components don't need to have such precision of power supplies. I could still use a single power supply, and the voltage divider rule would be able to give the power supplies required for the operation amplifier to work at very low voltages and still be able to do the job of precision operation, in this case of measuring voltages, of sensitively amplifying signals like an EMG, or taking a a temperature signal from a thermocouple. Okay, so we would see more about this in practical aspects. If you're interested in the session, or if you have any questions, you can feel free to send a message across to us, and you can reach me on my number 900-314-1931, or my email address simon@gemspolytechnic.edu.in. More details at the end of the video. Thank you and have a great day.